Hi and welcome to the next lesson in the Debugger series. Today's lesson's topic is Debugger's Introduction. Objectives of this lesson. We will study about what is a debugger, why use a debugger, and also about common mechanisms used by debuggers. Let's begin by what is a debugger. A debugger is a program that is used to test and examine other programs dynamically. Whenever we talk about debugger, we probably mean two programs. One program is the debugger, and the other one is called the debuggee, or the target program. Maybe in a picture, this is a debugger, and another program called the target program. Usually the program that you want to examine will be the target program. This will probably be your program that you want to check using a debugger. The debugger controls the target program, which means that the debugger can pause or continue the execution of the target program. It can also read or change the internal state of the target program, which means that it can change both memory or registers contents. There is nothing really special or magical about the debugger program. It usually gets help from the operation system and from the processor to have its special features of being able to pause and continue execution, or also to read or change the internal state of a program. These are usually things that come from the operation system or from the processor. Some words about different types of debuggers. Low-level debuggers are different from high-level language debuggers. High-level debuggers inspect high-level constructs, and those are language dependent. For example, there are debuggers for the Python scripting language and also for Ruby, Lisp, and so on. As opposed to those debuggers, low-level debuggers deal with assembly instructions and raw memory. We are only going to deal with low-level debuggers in this course. Why use a debugger? Two main reasons. Using a debugger allows us to understand how a program works. That is because dynamic analysis gives much more information, usually. If you only look at the code, you only see the general way in which things are going to work. However, if you perform dynamic analysis, you actually see the numbers inside everything. You see the numbers inside the registers. You can see the contents of the memory. Usually it will give you much more information and sometimes new insights about the program. Another reason is to find and understand bugs in your code. Sometimes there will be some problem in your code. Maybe you made some mistake. A debugger could be a good option to look for the bug or for the program and try to find out how to fix it. Generic operation of debuggers. The target program, the program that you try to analyze, is always in one of two states. It is either paused or running. When it is paused, nothing happens. It just waits on some instruction. When it is running, it executes many instructions, just like a usual program. The target is usually launched in a paused state by the debugger. We've already seen this in the first example. Whenever you launch a program in WinDBG, it will usually begin in a paused state. It will just wait. It will wait for commands from the debugger. During a pause state, the debugger can do a few things. It can read the internal state of the target, or maybe change the internal state of the target. it can also set future conditions for pausing the target program. This will allow the debugger to pause the program in the future in some desired state. The debugger can also ask the target program, to resume. Whenever the target is running, the debugger waits, and vice versa. If the target is paused, the debugger wakes up, and he can do all those kind of different operations. This is a schema or a picture of the generic operation of a debugger. The target has really only two options. It is either paused or running. Whenever the target is paused, the debugger can do many things. It could, for example, read or change the state of the target. It can also set future pausing conditions. Finally, it can also ask the program to resume, and then the target program will change its state from being paused into the running state. During the running state, the debugger cannot do much. Basically, it can only wait until the target is paused. Why would the target ever pause? Probably because of future pausing conditions. Maybe we put some kind of breakpoint, and after some time, the target will arrive at this breakpoint and it will pause. Another way to pause would be to just break it in some random place, which means that basically we can do another thing. We can also break from the running state. But if we do it, we will usually just find ourselves in some random state, which is usually not what we want. Basically, the only meaningful thing which we can do in this running state is just wait. Some people ask, how come during the running state we can't do more things? Maybe, for example, how come we can't read or change the state during the running state of the target? Let me explain this by some kind of analogy, which is the blender analogy. Assume that you want to make a fruit shake using a blender. The blender has always two different states. It can either be paused, which is this state, or it can be in the running state. During the pause state, we can do many things. For example, we can look inside and understand what we see inside. We can also add or remove fruit. And maybe, for example, we can also clean the blender. Finally, we can start the blender, which will take it to the running state. During the running state, we cannot do much. Basically, we can just wait, or maybe stop the blender, and then it will stop at some random point. Basically, during the pause state, we can really look inside and understand things. However, during the running state, we cannot understand what we see, because everything is too fast. Also, we cannot clean the blender while it is running, and that is because it is dangerous. Things happen too fast, therefore we cannot touch it when it runs. We can only do modifications whenever the blender is stopped or paused. This is exactly the same as the states of the target. Whenever the target is paused, we can do many things. We can change the state or maybe read it. However, when the target is running, we can only wait. That is because the target is running really fast and we cannot see anything. It is also too dangerous to try to change something whenever the target is running. The target's pause time. As we have already seen, most of the interesting things could be done while the target is paused. Some things that we can do. We can read or change registers, and as a specific example, we can even change EIP, which means that we can change the current location of execution of the program. We can also read or change memory. And finally, we can set future conditions for pausing. For example, we could add a breakpoint, which will only trigger in the future, after the target will be back in the running state. The idea of stepping. We've already seen this in the example. Let me explain in a more detailed way what is stepping all about. Stepping is about resuming for only one instruction and then immediately pause. By stepping, we can execute instructions one by one. We only execute one instruction at a time, and then we can see the effect of this instruction on the total state of the target. We can see the modifications to the registers and also how the memory has changed. Most modern debuggers support stepping. Usually it is the most basic feature of a debugger. This is what people usually think of when you tell them that you use a debugger. They think about the stepping feature. Most debuggers will distinguish between two types of steps. The first one is called step into, and the second one is called step over. Step into stands for step into functions, and step over stands for step over functions. Whenever EIP points at some call instruction, if you use step into, the next instruction that you are going to see is the first instruction of the function. However, if you use step over, the debugger will execute all the instructions inside that function, and it will pause right after the call instruction. Let me show an example to emphasize those two kinds of steps. We begin with stepping into. Let's assume that this is the target program. We have some instructions here, then we call some function, and finally we have more instructions. This is the function, which is called simple func. We begin with stepping into. Whenever we get to a call instruction, if we step into, the next place where we are going to be is here, inside the first instruction of the function. Finally, we are going to get back outside. This is how step into is going to work. Next, let's talk about stepping over. Stepping over will have exactly the same effect as stepping into for usual instructions. However, when we get to a call instruction, if you step over, the debugger will not care to take you to those instructions inside the function. It will just execute all of this function really fast and get you here to the next instruction. This is the effect of stepping over. Sometimes you will want to step into if you really care about what a function does or how it works. However, sometimes you will not want to do it. One important example would be input and output functions. Usually you will not want to step into those kind of functions because you don't really care how they work. You will also usually not step inside code which is not yours. That is because you didn't write it and usually you will not care about it. Sometimes you will, but for the most part, you will not want to step into, for example, system functions. For example, you don't want to step into exit process. Usually it will not be so interesting for you how exit process works. You just want to know that it does work. Software breakpoints. The basic idea of software breakpoints is that the target program will pause whenever it gets to some specific instruction in some specific location. You really tell the target program, pause whenever you get to this instruction. Breakpoints could be set only during the target's pause time. You cannot set breakpoints during the target's running time. It is not possible because the target is running really fast. The general workflow when using a debugger will be as follows. We first set up a few breakpoints in a few interesting places, and we do it during the target's pause time. Then we let the target program run. After some time, we expect the target program to reach one of those breakpoints, and then it will pause. At this point, we will be able to inspect whatever we want to inspect. Maybe, for example, we care about the values of some registers at this point, or maybe we want to see the contents of the memory. How do software breakpoints work? Software breakpoints are based on a special instruction called int3. This instruction is also known as a trap to the debugger, and it is encoded as 1 byte, which is CC in base 16. The debugger wakes up whenever this instruction is invoked, which means that if you put this instruction inside your program and you debug it using a debugger, if the program is running, whenever it gets to this int3 instruction, the program will pause and the debugger will wake up. This is a special way to move the program from the running state to the paused state. I want to note that this instruction has the special feature of being encoded as only 1 byte. We are soon going to see why this feature is really useful. Let's look at an example. Let's assume that this is a part of the target program. On the right side, we can see the instructions, the textual representation of the instructions. On the left, we can see the encoding of those instructions. This is the numeric representation of each instruction. Let's say that we want to break or maybe to pause whenever we get to this instruction. In other words, we want to have a breakpoint at this point. We want to break exactly at this instruction. Let's see how the debugger is going to do it. It will first replace this instruction with the int3 instruction. I want to show it again. Originally we had this instruction, sub EAX EDX, which was 29 D0. The first byte is going to be replaced by CC, which is exactly the instruction int3. Here we can see that it is really useful that the int3 instruction is only of size 1 byte in memory, because we could put it in place of every first byte of any instruction. We can also see that we have leftovers from the instruction that we had here before, which was sub EAX EDX. This is the D0, and we have it as a leftover here. And we don't really care about it. We only care that we have the int3 instruction, because we just want to pause at this point. The debugger will also care to remember the original opcode, which was 29D0. That is because after we pause the program at this point, we want to restore the original instruction because we don't want to ruin the program. We want it to continue to run just as it should. Now let's see what happens when the program runs. We begin from this instruction. We continue to the next one. And then we get to int 3. At this point, we can do whatever we want. Maybe, for example, we want to inspect the values of some registers. Maybe we want to know what is the current value of EAX. As another example, we might want to check the contents of the memory, or maybe even we want to change the value of EAX. At this point, we can do all of those things, because the target program is paused. After we have finished with everything that we want to do at this breakpoint, we let the program continue. At that point, the debugger is going to restore the original opcode, which gets back the original instruction, sub EAX EDX. And the execution is going to continue as usual. Usually, modern debuggers do not expose you to the int3 replacement process, which means that you are not going to see all of those replacements and all of those things. You will just put a breakpoint and all of this process will be transparent for you, which is something to be pretty happy about. The debugger does the replacement and reconstruction for you. Summary of this lesson. We've seen that the debugger is a tool to help you understand code and solve problems inside your program. The debugging process is always about two different programs, the debugger and the target program. The debugger controls the target program. The target program is always in one of two states. It is either paused or running. The stepping feature of the debugger allows us to run the target program instruction by instruction. Software breakpoints wake up the debugger whenever a specific instruction is reached, and this is a very important mechanism. It allows us to choose a few states or locations where we want to pause and only deal with those places instead of having to step ourselves until we get to the correct location, which could take a really long time. This was a general introduction to the idea of debuggers. See you on the next lesson.